Okay, for this video, I'm going to go ahead and go over the first part for the video that I just went over for Lordia's benefit. Okay, vectors. We have two kinds of vectors. We have scalar and we have vector quantities in physics. Scalar is magnitude only. It would be like time. There's no direction to time. It would be like a number, like the number 3. It only has a magnitude. It does not have a direction. Vector quantities have magnitude and have a direction. Okay, magnitude and direction. This would be like velocity, okay? Like you're going 5 miles per hour to the north or to the south. So it has a direction. You can use vectors to solve for force, okay? As long as there is a direction, vector quantities can be, we can use vectors to solve for vector quantities. So let's say we have 3 arrows. The arrows represent the vector quantities. There's a tail and there's a head. So whichever way the arrow is pointing, that's the direction of the movement or the vector. So it has magnitude and direction. To signify magnitude, the longer the arrow, the greater the magnitude. So this one is longer than this one. So this has a greater magnitude than this vector. This vector would have a greater magnitude than this vector. So if a vector quantity has magnitude and direction, then this would be a greater magnitude than this one, and all 3 of them are going the same direction. So by now you should have opened up the pHet lab using the link that I have in the Schoology assignment. And by now you should have played with it a little bit. If you haven't, go ahead and take time, play with the simulation and see how it works. Drag vectors over, play with it, push the buttons, see what they do, see how this works. So go ahead, once you get finished playing, and check the values, the angle, and the grid check boxes. You can go ahead and click on this component button. Okay. So first thing we're going to do, it says I'm on number 5. Drag out a vector and move it until the tail is located on the origin. So grab a vector, move it over here, and put the tail on the origin. Click on the head of the vector and drag it until it is completely horizontal, points to the right, and has a magnitude of 20. So go ahead and do that, and it should look like this. Okay. Now think back when you were plotting lines in math. Okay. You're going to relive the days of plotting lines and Pythagorean's theorem. So look at the chart at the top of the page, right up here. Wherever you see a variable with an arrow on top, so it looks like this, or in this case, so you can see it. This represents the length of the arrow, okay? And just like we said over here, the length of the arrow signifies the magnitude of the vector. So the larger this number is, the longer the arrow is, and we say it has a greater magnitude. Okay, the theta, which I just drew over, the theta represents the angle of the vector in relation to the horizontal, to the x-axis. In the first example they gave us, it's completely horizontal. Okay? And A of x and A of y. It's the x component and the y component. If you'll remember, any line you draw on a graph that originates at the origin, you can drop down a vertical and come across with the horizontal lines. Okay? Those will be in relation to the x-axis and the y-axis. Those are your x and y components. Make sense? Okay. So, for this first one we drug out and put on the x-axis. What is the magnitude? Anyone? Come on. Yes, 20. Okay, they're right up top. What's your angle? 0, because it's a horizontal line. Okay. Your A of x, what's your horizontal component? 20. And your vertical component? 0. Okay. It's 0 because all of whatever we're measuring is on the horizontal plane. There's no up and down. There's just left and right. Now, it wants you to drag out a second vector. I will go ahead and tell you whichever color vector you picked first, stick with it. So I pulled a blue one, so I'm going to pull out another blue one, put the tail at the 20, and put the head up at the 15. Okay? This is our second vector. We'll call this vector B. So the first one we did was vector A. We'll call this vector B. So vector B, what's its magnitude? 15. It's how long it is. Just follow along. Don't make it complicated. We had to start somewhere, so we're going to build as we go through this. What's the angle? 90 degrees. Okay. What's your x component? 0. All the movement is up and down. There's no left or right. And your y component? 15. Does that make sense to everybody? Yes. Where we got the numbers? Yes. Okay. Now, as you saw in the previous activity, if you were to walk this path, at the end, you would be 25 units away from the origin. So if I were to walk the 20, then walk to the east, and then I were to walk 15, whatevers, I'm assuming meters, to the north, I will end up 25 whatevers, meters, let's say, from where I started to where I ended up. To verify this, whichever color that you chose to pull out, hit the sum for that one. This button right here. And what it does is it calculated what the hypotenuse would be. Now, this is a part that I'm trying not to confuse you on. Where it says that you are adding vectors, it is true. You're going to add this vector plus this vector, and the answer is 25. Okay? But you're not really adding them like you're thinking 1 plus 2. You're adding them in the sense that you're using Pythagorean's theorem. Remember, Pythagorean's theorem only works on right triangles. So, assuming this were drawn straight, let's say it's a right triangle. This is your A, this is your B, and this is your hypotenuse. Okay? Remember, A squared plus B squared equals C squared. In physics, the C is the resultant. So if you hear me say the resultant, in your mind, you can either think C or you can think hypotenuse. Okay? In math, we call this the hypotenuse. In physics, we call it resultant. Okay. So technically you are adding this vector and this vector to get this, but between you and me, you're using Pythagorean's theorem. It does involve addition, but it also involves a square root. So it's not exactly 1 plus 2. Okay, clear as mud? So 25 units, you can show this by clicking the button that says sum. The new dark blue vector S, that's this one right here, should show up. This represents the vector sum or resultant of the first two arrows, or the first two vectors. So in terminology that you're going to hear, we've just added those two vectors to get the resultant. Okay? This could have been force, this could have been velocity, this could have been in meters. As long as all the vectors are the same, you added the two vectors. So drag the vectors over so that the tail is at the origin and use it to form the hypotenuse of the right triangle. Already done that. Notice that the head of this vector exactly matches where the second vector ends. Click on the dark blue vector and fill out your chart. Okay, so for the hypotenuse, what is, or the resultant, what is the magnitude of the resultant? 25. What is the angle of the resultant? 36.9. What is the x component? 20. And what is the y? 15. Okay, next question. I'll go ahead and tell you now that it says values from question 10 and 11. The numbering is messed up. You're going to compare 10, 7, and 8. So 10, 7, and 8. What do you notice about from this one we just filled out in the top two charts? Okay, I'll give you a hint. The legs, okay, let's see if I can say this so I won't confuse you. The legs of the resultant, if you drop the vertical and you come across with the horizontal, they are the same as your original two vectors. I mean, you may be thinking, well, of course it will be. But had we had more than two vectors, this may or may not have been the case. The overall legs from where you started to where you ended up, if you had more than two vectors, when you find the resultant, you would drop it down to the main axis and come across. So basically what it's telling you, if you know the two legs, you can calculate the hypotenuse. If you only have the hypotenuse and let's say the angle, you can use sine, cosine, or tangent depending on what you have, what you know, and you can calculate what the two legs were. Okay, so here we calculated it forward to get the resultant. You can have the resultant and calculate it back to get the legs. Okay, so, and this first is pretty straightforward. Now go to the next page. Now we're going to take it another step. Hit the all clear button. Okay, so let's clear it again. Next, create a new vector with an x of 20 and a y of 15. So here we go again. Here's our 20 and here's our 15. There we go. Go ahead and fill in your chart. So your magnitude is what we're talking about for the resultant here. What is the magnitude of this line? How long is it? 25. What's its angle? Still 36.9. And its y is what?
15.
The y, the horizontal going across, is 20.
That's the x, isn't it? Yeah, that's the x.
I'm sorry, I meant the x. Sorry. So the magnitude of A is 25. The angle is 36.9. The x component is 20, and the y component is 15. Sorry. So compare the chart values of this vector to those of the blue one from the previous question. How do they compare? Well, they are the same. Easy answer. They're the same. So now it wants you to click on this button so it can drop down the X and the Y imaginary lines. Mine won't let me. Well, this is what it should have looked like. Hit this button, it drops you down and shows you the two vectors, the X and Y components, I should say. So now you're going to adjust your vector. You're going to move the vector until the value of X is 15 and Y is 30. You're going to do it. You just can use the same one. I'm going to use a different color so I can explain, so I can compare and contrast. So I want my X to be 15, and I can't go up to 30, just go to 25. They didn't give us a large enough graph paper. So do 15 and 25. Okay. So in theory, we took this one and we moved it up there. So for your new one, what's the magnitude of the new one? Look at the top. What's your angle? 59. Your X component? 15, and your Y is 25. Okay, new numbers. So did the magnitude change? Yes. Okay. It went from 25 to 29. Did the angle change or the direction change? Yes. This was 36.9. Now it's 59. Whereas it was pointing towards the corner of the graph paper, now it's pointing upwards. Okay. So figure out a way to adjust the magnitude and the direction of this vector. Okay, so this one, take the one you adjusted and readjust it until it has a magnitude of 25, but in a different direction. So it was here. Choose a different direction, but make sure the magnitude is still 25. So find a position to where we're back at 25 now. As long as you come in close, because this is clicking to the graph paper. Oop, there I go. Okay. So find another triangle. Everybody's is going to be different. There's no right or wrong answer as long as your magnitude here is 25. In my case, I mean, you could have drawn it off to this direction. Most of what we're going to do is going to be in this first quadrant, but there's nothing to say it couldn't be in the second, third, or fourth quadrants. So in my case, my magnitude or the length of the resultant is back at 25. In my case, my angle is 16.3 degrees. My Y component is 24, and my X component is 24. My Y component is 7. Okay. So it's wanting you to figure out that these are not set in stone. As long as you can form the right triangle, the others can be flexible. Just because your resultant is 25 doesn't mean your legs are always going to be 20 and 15. In this case, I still have a magnitude of 25. I still have a right triangle, but my legs are 7 and 24. Okay? Now, tomorrow, after our activity here in the classroom, we're going to continue on, and we're going to continue where we're at right now. Look at this vector, and we're going to apply the sine, cosine, and tangent to calculate what we don't have in certain problems, depending on what the problem is asking for. So you get the review of your triangle geometry tomorrow. Any questions? You got it? Okay.